Let's discuss numeric PDE solving over regions. In Mathematica, you have the functions ndSolve and ndSolveValue to compute solutions of differential equations. In this example here, I use ndSolveValue to compute the solution of a Laplacian z equals to 10. This is a Poisson type of equation. The dependent variable is u, and x and y are the spatial coordinates. Additionally, two boundary conditions are specified. At y equals 0, the dependent variable is set to 0, and at y equals 1, the dependent variable u is set to 1. U, again, is a dependent variable, and the region is specified as x going from 0 to 1 and y going from 0 to 1. ndSolveValue will return an interpolating function. That interpolating function can be used in functions like plot3D to visualize the result. To solve PDEs, typically you need to specify three things. You need to specify the region omega. Of course, you need a PDE that you'd like to solve. And thirdly, you need to specify boundary conditions that interact with the PDE and the boundary. Here's a second example. The region we'd like to solve the PDE over is a disk, omega. The operator is the negative Laplacian -1, and we specify a Dirichlet boundary condition that says that the dependent variable u is supposed to be 0 for all values of the region that x is larger than 0. Again, we call ndSolveValue, set the PDE operator to 0, give the Dirichlet boundary condition as an argument, u is a dependent variable, and x and y are element of omega, which is the disk in this case. Again, ndSolveValue will return an interpolating function, and we can again visualize that solution with plot3D. Note that in this case, the region was not rectangular, was specified to be a disk. Let's discuss the specific PDEs that can be solved with ndSolve or ndSolveValue. The coefficient form is the most generic PDE that can be solved. It has a first-order time derivative and several different spatial derivatives. If one looks at specific equations, for example, the Laplace equation, then the coefficients that are active are highlighted in blue. In this case, in the Laplace case, c is set to 1 and f is set to 0. A Poisson type equation differs only in that the right-hand side f is not 0, but a specific value. The Helmholtz equation has an additional term plus au. A convection reaction type equation has additional terms beta.w plus au. A heat equation is a time-dependent version. A wave equation has a second-order time derivative, and ndSolve will convert higher-order time derivatives to systems of first-order PDEs. These coefficients, c, alpha, beta, gamma, and a, f, can all depend on space and time. Let's look at the Poisson type of equation. In the picture below, you see a red and a blue boundary. We'll modify the specific PDE and the boundary conditions to first use two Dirichlet boundary conditions on the red and the blue boundary, and then a Dirichlet and a Neumann boundary condition. Let's set up the problem. First, we specify an implicit region that models the exact region we've seen just now. The operator is a negative Laplacian -20, and in this first example, we specify that the Dirichlet condition u, the dependent variable, is set to 0 at x equals 0 and y is between 8 and 10. So that's the left and upper corner of the region we just saw. The second Dirichlet condition sets the dependent variable to 100 and is on the half circle set on the region. We then call ndSolveValue with the operator set to 0, the Dirichlet conditions, the dependent variable u, and x and y, element of omega, and omega is the implicit region. We visualize the result. UIF is the interpolating function returned by ndSolve, and the solution is depicted below. Currently, we have three different types of boundary conditions. There are Dirichlet conditions, generalized Neumann values, and periodic boundary conditions. Dirichlet conditions specify that the dependent variable u is supposed to have a specific value on some part of the boundary. Generalized Neumann values specify a flux over an edge on some part of the boundary. Also note that if on some part of the boundary no boundary condition is specified, then a generalized Neumann value of 0 is used as a default. And thirdly, we have periodic boundary conditions. Those relate the dependent variable u on specific different parts of the boundary in some relation. Let's look at the previous example again. We use the same region and the same PDE operator. Now we specify a Dirichlet condition where we specify that the dependent variable u is supposed to be 0 at the specific boundaries given here. That corresponds to the upper left-hand part of the region. Next, we specify a Neumann value on the semicircle that's the inner part of the region. We can then use undissolved value and specify that the operator is the same as the Neumann value, have the Dirichlet condition, and u the dependent variable, and x and y are element of omega, the region specified previously. And we can visualize the result below. Let's look at the theory of boundary conditions. In this illustration, you see an arbitrary shaped region which has several boundaries. The outer boundary, boundary 1, is the outer part of the region. Then there's an inner boundary, in this example a hole in the region, that's boundary 2. And there's a third boundary, that's a material boundary, boundary 3. Dirichlet conditions and Neumann values can be applied to specific parts of the boundary. The Dirichlet conditions, here depicted in blue, can be applied at the outer boundary, at inner boundaries, and at material boundaries. Neumann values, on the other hand, can be applied at outer boundaries or at inner boundaries. Typically, the normal vector is outward pointing. Also note that Dirichlet condition and Neumann value take two arguments. The first argument specifies either the Dirichlet condition or the Neumann value, and the second argument specifies the predicate where on the boundary that condition is supposed to be met. Let's look at the theory of Neumann values. For that, remind yourself of the coefficient form we've seen earlier. Note that there's a close correspondence between the Neumann value and the coefficient form. I'm going to try to explain where this correspondence comes from and why it makes sense. For this, we look at the very simplified version of the finite element derivation. For that, the coefficient form is taken and multiplied by an arbitrary test function phi and integrated over. That means that the finite element method actually tries to find the solution to the PDE in a weak sense. Now, that expression is integrated by parts. Doing that gives two interesting properties. First, note that the differentiability on the function phi is increased by 1, but the differentiability request on this part of the integral is decreased by 1. Also note that we now have a boundary integral. The coefficient c in this first part of the expression and in the boundary expression is the same as our alpha and gamma. Now what happens is that this part here of the boundary integral is replaced, is substituted with the definition of the Neumann value. Here's an example for a periodic boundary condition. The region we're looking at is made up of a rectangle. On the left-hand side, a disk is added, and on the right-hand side, a disk is subtracted. The PDE operator is a negative Laplacian, and it has an additional load term. That load term is active, it gives 1 if it's inside a specific part of the region, and 0 if it's outside of that region. Now, periodic boundary conditions take three arguments. First, the dependent variable and the relation of how that dependent variable at the target is supposed to relate to the values at the source. The second argument is a predicate where the periodic boundary condition is true. And the third argument describes how the values of the predicate, where the predicate is true, are supposed to be transformed to the source, where the dependent variable then is evaluated and used in the further computation. So what we have here is we have a target at the blue boundary, and the green bar boundary is where we'd like to evaluate the dependent variable u. So for this, the dependent variable is specified simply as u. The target is specified at x squared plus y squared equals 1, and the function x plus 2, 0 maps all points from the blue target to the green source, where the final dependent variable is actually evaluated. As a second boundary condition, we have a Dirichlet condition that specifies that the dependent variable is 0 for the top and the lower bottom of the region. When we solve this with ND-solve, we proceed as before. We specify that the operator is equal to 0, give it the periodic boundary condition and the Dirichlet condition, specify the dependent variable, and x and y are part of the region. In the picture below, you see several of those regions connected together to show the periodicity of the solution. Let's look at the transient problem. Imagine a pipe. Inside the pipe, we have a hot liquid, and outside we have room temperature. Now, additionally, in the pipe wall, there are cooling ducts to cool the pipe as such. The specific region that models a symmetrical part of that pipe is depicted below in blue, and the mathematical description is given as a implicit region. To model this, we use the negative Laplacian of the dependent variable u that now is also time dependent. We specify two Dirichlet conditions, one on the inside and one on the outside. At the inside, the dependent variable u is set to 200, and at the outside, the dependent variable u is set to 15 degrees. The Neumann value models the amount of energy that's absorbed by the cooling liquid. For times t smaller or equal to 10, the amount slowly grows until it reaches its maximum. Now, to solve this, we call ND-solve value and specify these operators at time t equals 0. That will give us a suitable initial condition for the temporal problem. We then call ND-solve with the time derivative of the dependent variable u plus the Laplacian operator and set that equal to the Neumann value, and additionally specify the Dirichlet condition. These are time independent, so it doesn't matter at what time those are specified. Additionally, we also specify the initial condition at t equals 0. T goes from 0 to 25, and x and y are part of the region specified above. Below, you see a visualization of how the cooling liquid affects the temperature distribution in the wall of the pipe. Here's the second visualization, where the contour plot of the temperature distribution in the pipe is put back into the original region that I've shown at the start. Let's look at a wave equation. The wave equation has a second-order time derivative of the dependent variable u. The special thing here is that the region is rather complicated. I have a rectangular boundary and some writing inside of that boundary. What you see a little further down here is a POV rendering of a solution of the wave equation in that domain. The letters are a hard boundary, and the wave refracts from that boundary. All of this has been computed with ND-solve. Only the rendering has been done with POV ray. This usually takes about 50,000 elements and computes in about 5 minutes. The render time is around about 5 hours. Here is an animation of that wave equation problem in that specific region. In the next few slides, I'd like to explain how the wave equation can interact with different boundary conditions. For that, it's important to know how ND-solve deals with higher order time derivatives in general. These are typically converted to systems of first order. So if we have in this example a second order time derivative in the dependent variable u equals to some PDE operator, that is converted to a first order time derivative on the dependent variable u equal to v, an auxiliary variable. And that auxiliary variable v has a time derivative which is then set equal to the PDE operator. Let's look at a specific wave equation. So we have a second order time derivative on the dependent variable u minus a Laplacian. We have an initial condition and we set the derivative of the initial condition to 0. If we solve this with NDSolve and animate the solution, we get the following. We see that the wave bursts out and gets reflected at the boundaries. This may be what you want, but it may also not be what you want. In this second example, we set the derivative, the temporal derivative of the dependent variable u to 0. That is specifying a Neumann value for the auxiliary variable as shown earlier. So an absorbing boundary condition can thus be modeled. Now, when the wave runs out, it's absorbed at the boundaries. In this third example, we try to use periodic absorbing boundary conditions. The problem setup is similar to before, with the only difference that now that the derivative on the initial condition is actually specified to have an initial velocity on the wave. So the wave is moving to the right in this specific case. We specify a periodic boundary condition where the dependent variable u is supposed to be taken from the right-hand side and mapped to the left-hand side. Looking at the solution, we see that the wave moves to the right and re-enters on the left-hand side. NDSolve can solve systems of n PDEs. In this example, I've chosen 2 PDEs with dependent variables u and v. The 2 equations are in principle exactly the same as the coefficient form given earlier, with the only difference that each of the equation depends on the 2 dependent variables u and v. This allows for cross-coupling between the different components in the PDEs and allows for a great variety of PDEs to be solved. The Dirichlet conditions now also depend on u and v, as do the Neumann values. As another example, let's look at Stokes flow. Stokes flow is a system of 3 coupled PDEs, and they're depicted below. We have u and v as velocity components and p as a pressure. The example we'd like to analyze now is a narrowing channel. On the left-hand side, depicted in red here, we have an inflow boundary condition that specifies the velocity in the u direction. The u direction is equivalent to the x direction. And on the right-hand side, we specify a pressure 0 at the outflow. Let's start with the problem setup. First, we specify the region omega with an implicit region. Then we specify the PDE. Stokes flow is a function that's appended at the end of this notebook and will return the 3 PDEs that we've seen just before on the previous slide. U, v, and p are the dependent variables, where u and v are the x and y velocity components, and p is the pressure. We set that to 0 in all 3 dependent components. Thirdly, we specify the Dirichlet boundary conditions. The first Dirichlet condition is on the left-hand edge, the inflow condition, and it specifies that the velocity in the u direction is given by the formula shown. The second equation, the second Dirichlet condition, is that u and v are both set to be 0 between the inflow and the outflow. So all boundary walls have a 0 velocity component in u and v direction. And the last Dirichlet condition specifies the pressure at the outflow. P is set to 0 here. To solve this, we call NDSolve value with the specified PDE and the boundary conditions. U, V, and P are the dependent variables, and ND solve value will return 3 interpolating functions. X and Y are part of omega, the region we just specified. And additionally, we specify that the method to be used is a finite element method and specify that the interpolation order for U and V, the 2 dependent variables, is second order, and the interpolation order for P, the pressure, is first order. That is a stabilization technique common in the finite element world. Lastly, there's a visualization of the velocity field of the inflow and the outflow part of the component. Let's look at the 3D structural mechanics problem. We have a graphics of a crankshaft. That crankshaft is held fixed at both ends, and forces from the piston deform the object. The problem setup. We first use discretized graphics to convert the graphics into something that 2-element mesh then can generate an element mesh from. The mesh order is set to 1, and this says that the approximation is first order accurate. This generates a mesh of 175,000 tetrahedra. You don't have to use 2-element mesh to generate the mesh, but you can. And in this case, I've just done this to illustrate to you that it's possible to do it. Second, we set up the PDE and the boundary conditions. The stress operator is given at the end of the notebook. It takes Young's modulus and Poisson's ratio, U, V, and W as dependent variables, and X, Y, and Z as the spatial coordinates. This will return a set of 3 coupled PDEs. The first 2 are set to 0, and the last one gets a Neumann value with a value of -1000. This means that the force is pushing in the negative Z direction at the given positions. Thirdly, we give the Dirichlet conditions where we say that U, V, and W are set to 0. They're held fixed at both ends of the crankshaft. ND Solve will then solve this PDE and boundary conditions in about 6 seconds on this specific laptop. The visualization shows the deformed crankshaft in red. In this section, we're going to discuss numeric eigenvalue problems. To solve numeric eigenvalue problems, you typically need 2 or 3 things. You need a PDE, a region specification, and sometimes boundary conditions. The PDE is given in exactly the same coefficient form that ND solve and ND solve value take, with a slight exception that you don't have a right-hand side f, but a lambda u, where lambda is the eigenvalue. Boundary conditions do not always need to be given. If they're not given, the problem is unconstrained, and if you specify boundary conditions, it's a constrained eigenvalue problem. Here's a simple example. Let's look at the negative Laplacian. To do so, we use the function ND eigensystem minus Laplacian u is the dependent variable and x is the spatial coordinate, and in the region of x from 0 to pi, and we'd like to compute 4 eigenvalues and 4 eigenvectors. Those are returned in vals and fons. The vals are depicted below, and those are the 4 eigenvalues computed for this system. Plot shows the visualization of the eigenfunctions. Here's a second example in 2D. Again, we compute the negative Laplacian. U is again the dependent variable, x and y are the spatial coordinates. This is a constrained eigenvalue problem, as we specify a Dirichlet condition and specify that u is supposed to be 0 all on the boundary. U is the dependent variable and x and y are part of a disk, and we'd like to compute 6 eigenvalues and 6 eigenfunctions. The eigenvalues for this system are shown here, and below are plots of the eigenfunctions. Here's an application example where we try to compute the acoustic eigenmodes of a car. For that, I've downloaded a picture from Wikipedia. The picture shows a Mini which has been cut in half. I used the image processing mask tool to generate a boundary graphics. That is the black picture with the white boundary below. I then use the function bound to discretize graphics of that boundary, which gives me a boundary mesh region. I can directly feed that boundary mesh region to ND eigensystem, and in order to compute the acoustic eigenmodes, I compute the negative Laplacian, the eigensystem of the negative Laplacian. U is the dependent, x and y are spatial coordinates. and I'd like to compute 6 eigenvalues and 6 eigenfunctions. Next, you see the second eigenmode overlaid over the car. Blue areas are low acoustic pressure and red areas are high acoustic pressure. Let's summarize the capabilities of numeric PDE solving over regions. We can solve PDEs with linear variable coefficients, transient systems, eigensystems, and the PDEs over these arbitrary regions can be in 1D, 2D, and 3D. Thank you very much for attending. We hope you enjoyed it.